Sound covered very quickly in seconds. Longitudinal wave goes, you make it by pushing this in the direction that the wave is traveling. So it just like clumps up, you push it. So that is a longitudinal wave. Compression wave, that's also a sound wave. So transverse waves or electromagnetic waves, I go up and move up and down, like showing here, but the wave still travels this way. That is perpendicular. So those are going at 90 degrees, transverse. Transverse means 90 degrees as well. So just make sure you remember that electromagnetic waves are transverse, sound waves are compressional longitudinal. The reason I don't count these here as antinodes as well is because these dotted lines are representing a standing wave going back and forth. So this is called a standing wave. The reason it's called a standing wave is it looks like it's standing still and it's playing in real time. It's just, remember, it's a periodic wave. It's going over and over and over again. We have these pulses coming from this frequency generator. It's creating constructive interference here and destructive interference here. These are called nodes where there's no movement. So remember, from node to node is a half a wavelength. So there's two equations that you can use. Let's use this one as an example. There's two rationales to solve this. Let's say this is a standing wave like I just showed in the previous picture. We only count the antinodes on one of these because it's vibrating back and forth. So the number of antinodes here is 3. That's n in this equation I'm showing you right now. That's my n. So I know if the length from here to here is 32.9, from n to n is 32.9, I can use my algebra skills and say this 21.93 meters, the length of one wavelength here. Another way to do this is if I know from node to node is a half a wavelength, that's a half, that's a half, that's a half, that's 1.5. So if I solve algebraic, so 1.5 lambda equals the L, the length of this entire thing. This entire thing is 1.5 wavelengths. If I just set them equal to each other, and then I get the same exact answer. Notice where they meet? They're meeting in different spots. That's where both waves are meeting. So at each one of these points, and it's coming up nicely, so they're all the green dots, that's where destructive interference is. This is how noise-canceling headphones work. So where they're meeting, that is where there's destructive interference. We have a string, we have a cup. Here's the string. Tension, the force of tension is pulling the string down, pulling it tight. So I'm going to take off one of these masses right here. So that's going to decrease the tension. I can adjust the length of the vibrating string. That's what you do in a guitar when you move your hands. You're adjusting the length of the vibrating string. Right now, sorry, it's hard to see, the length of this vibrating string is from here to here. It's pretty short. If I move it this way further, I'm going to stay in frame here. So now the length of the vibrating string is from my finger right here to where this touches the pulley right here. So let's play it. Pretty low pitch. I'm going to move it this way. Put my finger on it. Now the length of the vibrating string is from here to here. You should notice that's a higher pitch. Let's go. So I'm going to leave the length of the vibrating string the same. I'm going to keep that the same. I'm going to add another mass. That is going to increase the tension. How taut this is. So we can make a guess in your head right now of what it's going to be, higher or lower pitched, higher or lower frequency, and it is a higher pitch, higher frequency. These are the two equations for frequency and period. This is a little bit different than trigonometry definition of period. I believe that is the amount of distance it takes for one cycle to complete. In physics, we call this capital T a period, so it's the inverse. So remember, frequency is waves or oscillations or cycles or vibrations per second. So if you know the frequency, you know the period. And here's the rationale as to why behind all of this. So here I want to talk about the speed of sound, or in Mach 1, Mach 2. What does that actually mean? So it's all relative to what the speed of sound is. So what I want you to know based on this, then this y-axis, the speed of sound, the height or elevation in feet. So notice as my elevation increases, the speed of sound decreases. So think of it this way. If air is more dense, the closer to sea level they are, right, sound's going to travel faster. Think of that domino analogy I made. The dominoes are right next to each other. Here they're a little far apart. That's why it's harder to breathe at higher elevations, because there's less air up there. So there's less air, the speed of sound is going to be slower. So that's why it changes. It changes based on a multitude of things, but we'll just keep it simple with elevation and temperature. So if I say Mach 1 and at sea level, you're going the exact speed of sound. Notice there's no units because the units cancel out. If I'm going twice the speed of sound, I'm going the object is going 680, and the speed of sound is 340 at that elevation at sea level. Well, that's twice the speed of sound, so that's Mach 2. That's where that term comes from. So what I'm telling you guys is that the velocity is constant at the same elevation and the same temperature. So the speed of sound is constant at the same temperature, same elevation. That depends on the medium. So we're going to assume that the medium of the air is not changing.
Go! Hit it! Oh no, are you serious? No way. Are you serious?